So, hello everyone, and welcome back. This is episode 2.1, where we'll be looking into understanding linear regression and gradient descent. So, in this episode, we'll be looking into what is linear regression, a simple linear regression. Then we'll try to understand the gradient descent algorithm, which is the workhorse for any learning model. And then we'll look some variants of gradient descent like batch gradient descent, stochastic gradient descent, and mini batch gradient descent. Then we'll also see multivariable linear regression, or what we say multiple linear regression. But before that, let's have a recap of previous episode. So in the previous episode, I discussed about Keras, which is a higher level neural network library, and it enables very fast experimentation. Then I discussed about how we can install Keras by just simple step installing Anaconda, installing TensorFlow, and on top of that installing Keras. And then we spoke about, we can develop neural network model in Keras in two ways. Either one is sequential model and the functional API. So in sequential model is simply stacking of layers like this. And this is one example of code example of sequential model. We simply give the training data, we define the model, we compile the model, and then we simply train the model. Okay, and then we can with Keras you can evaluate the model, you can predict the model, any new test data with that same model. And with sequential API, with sequential model, you can define, multi-layer perceptron, you can define convolution nets, you can define LSTM nets, and with just few lines of code in Keras. So if you haven't watched the previous video, you can go and have a look at that. So another way in which we can create neural network model in Keras is through functional API. And through functional API, we can create complicated models like multi-input, multi-output models. And then we discussed that Keras can be used to implement regression problem, classification problem, and problems like object recognition and detection. And then we can also use Keras to integrate two different models here, like for image captioning we have integrated uh, let's say CNN and LSTM. And then in Keras there is also number of pre-trained models, and there is option that we can freeze different layers of weights, so it enables us to use transfer learning. And we discuss about how we can visualize the intermediate outputs in Keras, and then how we can save and load trained model in Keras. So pretty much that's all from previous episode, and in this episode, let's get started. So as we have discussed even earlier, that there are basically four types of learning. So supervised, unsupervised, semi-supervised, and reinforcement learning. And we mainly discuss about supervised learning. There are two type of tasks there: regression and classification. So supervised learning is a learning where we know the inputs as well as output, and a classification means categorizing between two classes. So if there are car detection algorithm, then we have number of training images of car, and we label them as car. Since it's supervised, we know its output. And we have lot of non-cars, and we label them as not car, and we train this model during training time. And at test time, we'll have a test image, we'll not know the output, and the model should classify whether it belongs to car category or the non-car category. And regression problem is a problem where we did not classify or categorize anything. Instead, we have to predict some number. We have to predict a real number or a real value. For example, we consider different temperature, and at that temperature how many ounces of water to consume. So if this is the data, the algorithm will kind of learn some model which will be some best fitting to this data, training data. And at test time will be given only the input, which is the temperature. For say there is no data of 30 34 degree, or 37 degree here, and based on the model we have learned, we can predict its real valued output. So this is what a regression problem is: predicting some real valued output. And this is one famous example: housing price prediction. It's from Andrew Ng. So given house sizes, these are the data of the prices, and then we have to learn some good model, and later given any new input x, it should be able to predict what's the new price. So we can summarize as linear regression is a supervised learning technique used to solve regression problems. Okay, So let's see. And so we can define, linear regression is a way of modeling between the dependent variables and the independent variables. So based on that, we have two type of linear regression. One is simple linear regression and one is multiple linear regression. So simple linear regression means we'll have a single input, like in this case temperature, and based on temperature we are predicting the consumption of water ounces. And another is multiple linear regression where we'll have more than one inputs, and based on this like multiple inputs we have to predict the output. So the inputs are the independent variable and the output obviously are the dependent variable. Okay, so in linear regression, or we are trying to create some linear model of the given input data x using some parameters we'll discuss later, that will learn the variances in data x, and it will try to learn a best fit model such a way that given any new data x whose y is unknown, it will be able to predict y. Okay, so this is a mathematical form of linear regression. So depending on number of inputs, we can have that many parameters plus one intercept parameter. So let's avoid this now and let's see this one. So you can actually relate between simple linear regression and equation of straight line. So if you remember, this is the equation of straight line, and it's given by y equal to mx plus c. Okay, so m is the slope of the line, so that gives the relationship between x and y, this m. And then c is the intercept, or the yeah, it's the intercept on the y-axis. So if c is 0, it will pass through origin, and if c has some intercept, it will pass through that intercept. And this is a linear regression model, simple one. So this also we can relate it to this equation of straight line. This is this is a line with intercept 0. So y is equal to 3x, its slope is 3, passing through all these data points. And with slope equal to y equal to 3x plus 1, it will be passing through all the data points, having an intercept of 1 here on the y-axis. So linear regression, simple linear regression is similar to equation of straight line. So let's take an example. So let's consider we have a given data of population of different city, and based on the population, what is the profit of a food truck there. Okay, so so this is the data points on plotting population on the x-axis and profit on the y-axis. Okay, so somehow we have to learn a model here, a linear model. So you can relate with this straight line here. And instead of using M and C, I'll be using weights and biases because that's a neural network term, and we'll be using this in the later videos. That's why I'll just start here. So the concept remains the same. Instead of M, we use W, and instead of C, we use B. Okay, and this is the Y is the model, that linear regression model that we have to learn. So we have to learn this regression line such that it's the best fit to this data. Okay, so that's our task. So yeah, this is our task. So to create a linear regression model, we need to know the parameters W and B. Okay, so since it's a supervised learning, we'll be knowing X and Y during the training time. So from this data, we have to learn W and B, so that in the later, like when we don't know Y, by knowing W, B and X, we can predict the new value of Y. And this W and B should be learned in such a way that this regression line is the best fit to this data. Okay, so so let's consider this. We have a population, we have a profit, X, Y. Now, since this Y is the training data, X and Y, the predicted model, I will not use Y, I'll use A. And this also because in future we'll be using A to, give the output of different neurons. So I'm just considering this from now. So it's the same thing. So we have to learn a model A, which is equal to WX plus B. And since we don't know W and B, we'll start with choosing random value of this W and B. So it's in linear regression you can choose 0, no problem. So this is our model. So we have an input X, and we have a model parameters W and B, and we have to compute A here, okay, based on this W and B. So consider for the first example, population 6.1101, and we have a random value of W as this. We multiply it, we add it to one bias term or the intercept term, and we get some output here. So this is the output 4.05505 of this input. But how will we know that our model is doing well? Well, now we can see that this and this is not same, but we have to somehow feed this into model so that the model knows that he is not doing well. So the so that's where supervised learning comes in. Since in supervised learning we know the true output during the training. So what it will do is that we'll take this predicted value and we'll compare it with the actual value which is in the data. Okay, and based on that we'll compute the error, and then the model will know that it's not doing well and it will learn. So we'll discuss the error function in the next slide. But one thing I wanted to discuss here is in neural network term, that given input x and weight parameters, we have one more step in between before we compute a. So that is the z step. So z will be same thing, w x into w plus b will get this, and on top of z we apply some activation function. But in case of linear regression we are applying linear activation function. So a is just linear of z, which is z. So a is simply what z is. But in neural network, it's not necessary that we use a linear activation function. We can use other non-linear activation function. In that case, a will be differing from z. Okay. So yeah, but don't mind this. I just wanted to give information here. In linear regression, a is same as z because it's a linear activation function. So we can just stick with this for now. So as we discussed now that we have computed a value which is w into x plus b, and we have given from this data. So this is the set of entire data, x1, y1 being first example, second example, and this is the last example. So the goal is that the predicted value by the model of the any example, I refers to the example, which number of data. So the predicted example should be very close to the actual or true value. Okay, so this is the our goal. So we saw in previous slide that this was the predicted and this was the actual, and how we can know that the model is doing mistake is by computing the error between them. So the best way to compute error here is taking the squared error function. So for example, for the one example, this is a, this is y, so a minus y squared, but we have m example. So what we'll do is we'll compute mean square error. So we'll pass all the examples and we'll compute the error, and then we average over the number of examples. So this gives the mean square error, and the overall error over all the entire training set is called the cost function. Okay, and our goal is to minimize this cost function. Okay, so I hope you are clear till now. If you are not, you can pause and you can have a look at this slide. So let me refresh everything what we have discussed. So yeah, so we'll be given data x and y. This is simple linear regression, so we have just one x and then we have the y, and number of input is 1, number of output is 1. So this is our linear regression model. Given x, we have to learn w and b so that we can predict a, which is w into x plus b. Okay, and so we don't know w and b, so initially we'll start by choosing some random value of w and b, and in linear regression we can use it 0, and based on this initial chosen parameter we'll predict some value for every data, all these data points, and then we'll compare it with the actual value from this given y, and then we'll compute the error between this predicted and actual value through squared error function, and we do it for all the example to compute the overall error function called the cost function. So this error which is caused, it is due to our initial chosen parameters w and b. So somehow based on this error information which we have to correct this w and b so that this difference between predicted and actual gets reduced. So that's our goal. Okay. So for this we are going to use a optimization algorithm, gradient descent. So if you have a look at this picture and this equation, so we have to get a model A equal to Wx plus B. We didn't know the value of W and B, so we initially chose some random value of W and B, computed A, and then we computed the cost function by comparing it with the true output, the predicted output with the true output. We got a cost function, and this was due to these parameters W and B from here. And if you plot it, you will see that the cost function as a function of weights and biases is some convex function. Okay, and our goal is to reduce this cost or this error. So if you see this, so this is the plot of the cost function j with respect to w. So anywhere we are, our goal is to reach here. Our goal is to get to this value where the error is minimum, where we get the best value of our parameters w and b. Okay, so that's what the goal of gradient descent is. And how it does is, given the cost function, it will compute the gradient of the cost function, doesn't matter wherever you are, and based on that gradient it will try to move in a direction of steepest descent. Okay, so if you are here, it will try to move downhill in this direction to the minimum minimum to the position where the cost is minimum, and if you are anywhere here, it will try to move to the left side here where the cost is minimum. So we'll have a look at this. Yeah, this is one small animation. So suppose if you are here, step by step in gradient descent over number of iteration, you move down, you move down, you move down till you get to the best value of the parameters where the cost is minimum. So this is another way, this slide from N to NG. So you know, gradient is an inclined part of road or railway. Let's consider a gradient is a slope. Okay, and it measures whether there is increase or decrease in the magnitude we are trying to measure. So let's take these two slides and so these two pictures. So let's have a look at this first. So we have to compute gradient, and gradient is the slope. So at this point we have to compute the slope. So we have to measure the change in y with respect to change in x. Okay, or dy by dx. We can measure this change in y with respect to change in x by subtracting the new value with the old value, and here also new value with the old value. Okay, so what's the value of y at x2, what's the value of x1, we'll subtract it and divide it, so we'll get a change or the slope. And this gradient that we compute, change in y with respect to x, is positive because y2 is greater than y1 and x2 is greater than x1, so we get a positive gradient. So at this place, the magnitude is increasing or the slope is rising. So let's consider this case. So here also we are going to measure the gradient or the slope, that is change in y with respect to change in x. So again we'll do y2 minus y1. So this change, and due to the change in x, x2 minus x1. So here if you see, x2 is greater than x1, so this will be positive, but the y2 value is less than y1, so this will be negative. So this gives a negative gradient, and it shows that your value is decreasing if in this direction. So this is a positive gradient and this is a negative gradient, and I'm showing you this because in gradient descent, doesn't matter whether you are at a negative gradient point or positive gradient point, your aim is to move opposite to wherever you are. Okay, so if you are at here, you will move positive. If you are here, you will move negative. Okay, so let's see this example. So this is the cost function with respect to w, and this is the w. So initially, suppose we are at this point. So we started with some random value of w, and we got a cost at this one. So what we'll do is we'll compute the gradient, the change in j with respect to change in w, and it will obviously be positive gradient. And our goal is to move, downhill. So how can we move downhill? So for this we have this formula. So this was the old value of w. So we'll update w equal to w minus this gradient which we computed, this change that is there, and this is positive, but our goal is to move in opposite direction. That's why we'll subtract. And then there is one more term, alpha, which is the learning rate, and it defines the step size that you are going to take. So you are going to move from here to here downhill, but what is the step that you want to take? By how much amount of this gradient you want to subtract it with the old w? So if alpha is small, we'll move from here to here, and if alpha is very big, we'll move from here to here. So this basically gives the step size. What is the size of the step with which will change the w to move downhill? Okay, So by this formula, we'll get the new value of W here, and this is the new value of W. So with this new value of W, we'll get new cost, and then again we are going to repeat this. We are going to compute the gradient, and then we are going to repeat this formula. We are keeping on subtracting this gradient from the old weight values, and we are getting the new values. So we'll keep on doing this till we come to the minimum value of cost the where the value of W is the best value, because here the gradient will be 0 and the weight will be this will be 0 and there won't be any change in weight. The weight will kind of get stabilized, and we'll say that we have got the best value of W here. Okay. But for our model, we have two parameters, W and B. So this I just showed you for W. We have to do this gradient descent for both W and B, and we have to get the best value for both W and B. And here the J will be function of W and B, because J is the cost function, which is the difference between the predicted value and the actual value Y, and the predicted value is a function of W and B. Okay, so this is how gradient descent works, and in this we have to get the best value of both W and B. So another point I want to say, suppose before I showed you the gradient was here, what if the gradient, oh sorry, what if the, sorry, cost, sorry. So what if the cost is here, okay? So we have some initial value of W, because of which our cost is here. So what we have to do, same thing, we have to compute the gradient here, and here it's a negative gradient, so dj by dw will be less than 0, and our goal is to move right side, okay? So our goal is to move downhill, and we can do by this formula. So here since this is a negative gradient and we always subtract, the formula always remains same, W equal to W minus learning rate into the gradient. But since it's a negative gradient, it will somehow this negative will become positive, and the new weight value will be this old weight value plus some item, so the weight value will move this side, so automatically it moves downhill. So, if that was a positive gradient, we just saw that it will subtract with the old value and it will move left. And if it's a negative gradient, it will like intrinsically add it and it will move to the right. Okay. And we are going to repeat this process. We are going to compute this gradient, and we are going to compute this formula, weight equal to weight minus alpha into this gradient, and we are going to move downhill till we get the best value of W. Okay. And in case of our problem, we have W plus B. So we are going to repeat this for both W and B till we get the best value for W and B. So this summarizes the gradient descent. And I hope you got the idea whether you are in positive or negative. The formula remains the same. So let me refresh it once again. So this is our data. We are given X and Y, and we have to, and these are the like all samples X1 to XM, etc., etc. Means it's going up to 1,000 or maybe I don't know many. And this is our model. Since we have one input, we have one parameter W and one B, and we have to start by choosing some random value of W and B. So we'll give this X, we'll choose some random value of W and B, and with this formula we'll compute some A value or the predicted value of this model. Then we are comparing it with the actual value, and we are getting this error function, and we do it for all the example to get the overall cost function, which we have to minimize. And we know that this cost or error is caused due to this weight value, so we have to somehow improve this weight value to reduce this cost. So then comes the gradient descent, where wherever we are with the initial value of W, we'll move downhill, we'll move towards the steepest descent, and we'll repeat this process over different iterations, and we'll update the value of W and B with this formula, W minus alpha into gradient, B equal to B minus alpha into the gradient, where alpha is the learning rate, which decide what is the step size that we have to take while moving the downhill. So when we reach here, we get the best value of W and B, and then we say that our W and B are trained, and we finally say that our model A equal to W into X plus B is a trained model, is a trained regression model. And now given any value of X, we know the best value of W and B, we can compute the output value. Okay, so this one picture summarizes the linear regression algorithm. So this is one animation I wanted to show you. So if you see this is a linear regression line, and initially at the iteration you just see here, at the iteration 0 the line was not good, but as we keep on improving, the line somehow learns itself and give the best fit. So initially the line was bad because of our weight value here where the cost was minimum, but as we train it over different iteration, it finally reaches here, and that's the best model. This best line over 800 iteration is due to the best value of W here. Okay. So once trained, we get the final model as this one, this line, and then we can predict any new value. Given any new x, based on the formula, we can predict any new value of y. Okay. So as I discussed, like the cost function JWB is computing this squared error and averaging over it. So what this was called as mean square error. But in practice, you'll see in all the like documents or implementation, they instead of using 1 by m, they use 1 by 2m. And that's because if you compute the gradient of this 2 will come here and 2 will cancel. The gradient of any x square is 2x. Okay. So this 2 and this 2 will cancel, and it gives kind of a very nice implementation. So the cost function will be written like 1 by 2m and sum over all the squared error function, all the squared error. Yeah. So learning rate is a very important hyperparameter. So this hyperparameter because it helps in learning the actual parameter w and b, and we have to be very careful for choosing the value of alpha. So if you choose the learning rate very high, so it will be taking a bigger step, and it will just bounce between the cost function. It will never converge, and in some case it will overshoot also. And if we are choosing a small value of this learning rate alpha, the updation of our parameters w and b will be very slow. It will be taking very small step, and if somewhere there is a local minima, there is also a chance that it may get stuck here. Okay, so we have to choose a very good value of alpha, the learning rate. So this is one animation here. So on the left side, if you see the value of alpha is 0.005, it's a small value. So it moves slowly till it reaches, the position of the, the what to say, the position of global minima. And this is an example where the learning rate is little higher than the previous one, and you can see this cost function is jumping between these two slopes, and it is never reaching the minimum value, or it is taking a really long time to reach the minimum value. So you have to choose very wisely the learning rate. And this is one from the Stanford. So if you have a very high learning rate, your loss function will somehow overshoot. If you and it may never converge. If you have very low learning rate, it will learn very slowly. And then if you have just high learning rate, it will just keep on moving between the two the two slope on both side, and it will just be constant, and it won't be reducing actually. So the good learning rate should be somewhat this line, so it should constantly reduce with number of iterations. Okay, so this is how it will look like in contour plot and this normal plot. So this is the cost function on the left, and as we train it over number of iteration, this cost function should reduce like this, and this also should reduce and reach this to the position of the global minima. So the over the training iteration, the curve should be like this. Then we know that our model is learning well. So this is another visualization. So we start somewhere here, we take step, we keep on taking different step till we reach, the position of global minima. And there are, I just discussed gradient descent. There are a number of different optimizers which are better than gradient descent, but the formula remains the same. The way you compute the alpha learning rate, that changes, and based on that the learning improves. So ada delta RMS prop and all, they are better than SGD. They learn very quickly over large, if you have very large training data. So now this is a different topic, we'll not discuss here, but the backbone remains same. The gradient descent, the way we update remains the same. The parameters may change. Okay. So the gradient descent have three variants of it based on amount of data that we are going to use for updating our weights and parameters. So there are three types: batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So a batch gradient descent is what we discussed, the vanilla gradient descent. So what it does is, as you know, to compute the cost function, so for every it's looping over all the iterations. For every iterations, it will compute the cost over all this example. Okay, so it will read all the example, take their error, and then take average, and then compute the cost function, and then it will update the weights and biases by computing the gradients of this. But what's the issue here is, suppose we have very big we have a very big data set. Consider you have 1 million examples. So for getting each update of W, it has to wait for a longer time because it will be, taking all the examples in consideration. So it gets really slow, especially when we have huge data set. Okay. So another solution here is a stochastic gradient descent. So in stochastic gradient descent means, instead of taking whole data set at once for computing the gradient and updating the weights and biases, we'll take one example for each update. Okay. So here we have a loop over iteration, and then we are going to loop over all the data samples. So for each data samples, we are going to compute this cost function, and we are going to update it. Okay. So in this case, the update will be the update of W value will happen very quickly because we are doing after every example. You are not waiting for the whole data set. However, here there will be lot of variances in the updation of weight because the error we are computing is based on just one example, and it will vary for example to example. In this case, we were taking average error, so that was more smooth or more good value of error rather than here. Okay. So the best solution is to go for mini batch gradient descent, where instead of just taking one examples or taking whole example here, we'll take a batch of example. So we'll suppose there are total of 100 examples in our training data, and we will take it over a batch of 10. So there will be 10 batches, and each batch will be having 10 samples, 10 examples. So batch 1 will have example 1 to 10, batch 2 will have 11 to 20, and so on, and batch 10 will have 90 to 100. So we'll be iterating one to number of iteration, and instead of every training example, we'll be iterating over one to number of batch, which in this case is 10. So here, instead of taking one samples, we'll take 10 samples, and this batch size I'm just taking 10. It may vary. It's a parameter you have to choose. So I'm computing this error over 10 samples, and I'm averaging this cost over 10 samples. So this cost which will we get, it will be a better value rather than this single example. So it will have less variances, and since it says like limited number of examples, it will not wait for all the entire training data set. The weight updation will also take place little quickly. Okay, and we'll get our values of W and B, learning of WNB will happen, very efficiently and quickly. Okay. So these are the three variants of gradient descent based on the number of data we'll be using to update our weights and biases. So this is one picture here. So this is a normal batch gradient descent. So this is taking smaller steps till it reaches here. But since we are averaging the error over all the training set, it goes very nicely. A nice curve is seen here. And this is the case of stochastic gradient descent. Since we are computing error over every example, it will be have a lot of variances. It will be jittering a lot, and that's because we have not averaged the error here. So this is another visualization. If we have weight here and we want to reach the minimum value here, in case of batch gradient descent or normal gradient descent, it will be little smoother the way we reach. And in case of stochastic gradient descent, there will be lot of variances, and there are chances that it will not reach to the actual minimum value because it will be jittering here and there, but it will be somehow close to the minimum value. And yeah, and this is another visualization of the same thing. It will be something like this in case of batch gradient descent, and in case of stochastic gradient descent, it will be jittering. And this one slide from Sebastian Ruder, it summarizes all the gradient descent. So first is batch gradient descent. Its accuracy is good. It converges to the global minima, but its update speed is slow because it takes all the examples for doing one update. So obviously its disk uses or memory uses will be very high. So especially if you have a very big data set, it won't be able to accommodate all the examples at once in your disk. And there is no online learning possible with this. In case of stochastic gradient descent, its accuracy is good. If because it's jittering a lot, if we anneal the learning rate later, then it may converge to somewhere close to the global minima. Its update speed is high because it's updating after every example. Its memory usage is low, and obviously online learning is possible. And the best one is a mini batch gradient descent. Its accuracy is good, its update speed is medium, and its memory usage is medium, and online learning is possible. Okay, so those are the variants of gradient descent. And this one slide, I want you to have a look at this once again. This is a simple linear regression model, and it's because I'm now going to scale everything this for multiple linear regression, and it's no difference, just one small change. So yeah, so let's go to multiple linear regression or multivariable linear regression. So in multiple linear regression, instead of having just one input, we may have multiple inputs. So consider this example: a different in sales of different company like Amazon, Google, Facebook, based on their advertisement on TV, radio, and news. So for every sample, we have three inputs and one output. Okay, so this output is based dependent on three independent inputs. And if we see a simple linear regression model as we saw in previous slides, A equal to W x plus B, here we are having just one input x, and we have one output A. Okay, so it's a 2D space, so we can visualize it as a straight line. But in case of this example where we have in this we are showing just two inputs, TV and radio, but there will be newspaper also. It will be a four-dimensional space, and it can be multi-dimensional space. There we have to, instead of learning line, it has to learn some hyperplane. So that hyperplane will be our linear regression model. Okay, and it will be decided by W1, W2, W3, and bias. Okay, said that, let's see how things work out for multiple linear regression. So we have this example: TV, radio, news, x1, x2, x3, and the output y. And we can represent this one as this. So x1 denote all these three, the first sample, x2 means the second sample, x3, and so on for all the samples. So our linear regression model here is like this: w1 x1 plus w2 x2 plus w3 into x3 plus b. So for each of the input we'll have a weight parameters, how much weight, how much weightage we want to give to those parameter, and overall bias. So we have three inputs and one output. So our model will look something like this. So we'll have three inputs, W1, W2, W3, and then we'll have A, W1 into X1, W2, X2, W3, X3 plus B. And since we don't know all these parameters, same as simple linear regression, we'll start with choosing some random value of these parameters. Based on this random value, for each example, this model will predict a predicted value A. Then we are going to compare it with the actual value Y, and on comparison, we'll get some error. And we'll do this for all the examples, over all the m examples, to get the overall cost function J. And J here will be a function of W1, W2, W3, and B, because J is computed by A minus Y, and A is a function of all these four parameters. So once we got J, how to reduce this J, or how to get the best value of our parameters? Again, is the same algorithm, gradient descent. So instead of updating for W and B, now we'll update at each gradient descent step for W1, W2, W3, and B. So for each of the parameter, we'll have a cost, we'll compute the gradient, and we'll update for W1 is W1 minus W1 equal to W1 minus learning rate into gradient of J with respect to W1. For W2, we'll subtract it with gradient, we'll take the gradient with respect to W2. For W3, we'll take this overall gradient with respect to W3. And for bias, we'll take this gradient with respect to bias. And for each of the four parameters, we'll repeatedly do it from here till we reach, the best value of W1, W2, W3, and B. And we say that our regression model, this one, is finally trained when we get the best value of our parameters. So this picture summarizes the multiple linear regression. So to summarize, in this video we saw what is linear regression, what is simple linear regression. We tried to learn linear regression model with gradient descent. We also looked into the variance of gradient descent, and then we finally looked into multiple or multivariable linear regression. Okay, and yeah, so these were the two examples we considered. For simple linear regression, we had the population of city and the profit based on the profit of a food truck based on the population of the city. It was a single input problem. And then we looked into multiple linear regression where we have three number of inputs and one output, which is the amount of units sold based on the advertisement of different company on TV, radio, and news. So maybe on the next episode we'll code these two problems. So tune in for the next episode 2.2 where we'll implement this linear regression using TensorFlow, and you can see how easily we can implement this model in TensorFlow. So pretty much that's all from this video. If you like it, then hit the like button. If you have any queries, you can comment below. If you want to get notified, you can subscribe. And if you want to support me, you can support me on the links of Patreon and PayPal given below. And till then, keep learning and keep exploring neurons.